All right, so we have a cyclist. They've given us a cross-sectional area, a drag coefficient. The cyclist is traveling, or riding rather, at a speed of 7.3 meters per second. So a steady speed. We want the cyclist's power output. So power, work per time, or energy per time. So if the cyclist is riding at a steady rate, if I were to draw the cyclist over here, the force that the cyclist is applying is counteracting the drag force they're experiencing. The steady speed tells us that the cyclist's force is exactly equal to the drag force that they are experiencing. So the work the cyclist is doing is their force dotted with displacement, but their force is what's propelling them forward. So force times displacement over time. But I'm not seeing a displacement or a time, so I want to look at the equation that has force and velocity. So force dotted with velocity, these are in the same direction, so I can simply multiply the force that the cyclist specifically is applying times the speed at which the cyclist is traveling. All right, so the force the cyclist is applying has to equal drag because they tell us in the problem that this cyclist is riding at a steady speed. All right, so we do need to go back to chapter 6 to find the equation for the drag force. And then we're multiplying by the speed to turn this into power. So this power is going to be 1/2 c rho a v cubed. The problem tells us the drag coefficient is 0.9. Rho, I'm just going to use the value 1.3 that was given in the test notes and in the chapter. A is the cyclist's cross-sectional area, so 0.45. It's in meters squared, so those are the SI units we want. And then the speed needs to go to the third power. 0.5. So 102, so approximately 100 watts is what this cyclist's power output is. So the rate at which that energy is put in, not just the total energy.